In the video 21 on the Foundations of Computational Economics course, we're looking at the practical problem of computing a stationary distribution of a Markov chain. Recall that a Markov chain is given by a stochastic matrix P, which denotes the transition probabilities of the states of the Markov chain. We will assume that the Markov chain will take values which are identical to the indices of the points in the state space. So it's going to be from 0 to n minus 1. We are using the standard Python base 0 indexing here. So the first element is indexed 0. We assume that that matrix P is nice, which is aperiodic and irreducible, and so there exists a unique stationary distribution, psi star, and of course it's given by this fixed point conditions. Psi star must be equal psi star times the transition probability matrix, and we're thinking of psi as a row vector. And so the task for today is to compute psi star. We know one method already from the previous video on Markov chains. Because we have the convergence result, we can just start from an arbitrary distribution, say psi naught, and then iterate by multiplying the current approximation of the stationary distribution to get the next approximation of this distribution. And then we can iterate on this multiplication until there's some kind of convergence, right? So we cannot distinguish the previous iteration from the current iteration anymore. So let's implement this first. Here's the setup. Let me print this. And I'll say that the separator should be a new line right away. So here's the transition probability matrix, and here's our, degenerate initial distribution psi. So it's like everybody starting in the first state of the state space. Right. So here's the function that we should implement. It's going to be called stationary SA for successive approximations. It will take parameters of the Markov chain, transition probability, the initial distribution, and then similar to the solvers that we've looked at in previous video, that was video 13 on the Newton method and the bisection method. We have the standard inputs for the solver, which is the maximum number of iterations and the tolerance level, and the callback, right, so that we can report something from each iteration. So in fact, let's take as an example the code for the Newton method, for example, right? So here we are. The main structure is going to be the same. So we will. This is just the call to check, right? So we will have the main loop up to the maximum number of iterations, and if the maximum is reached, then the else statement will run. And here we just raised the error that we failed to converge in so many iterations. Now there should be an update of the current approximation here, so we can say psi equals psi naught matrix multiplication with P. That's going in place of the Newton step. The error calculation needs to be different as well, right? So how do we know if we've converged? We need to compare the psi and psi naught, the two approximation, but these are vectors. So by looking at their comparison, we need to take the absolute value. Now this needs to be an NumPy version of the absolute value, so that we are comparing two NumPy arrays element by element. This needs to be less than tolerance, but because these are arrays, let's also take a maximum of all of the elements of this array. So Amax, I'm usually getting confused with numpy maximum. There's a function maximum which compares two arrays holding the elements to be compared. But there's also an Amax function, and the Amax takes one array and returns the maximum of the arrays of an array or maximum along an axis. Okay, so we want to compare the elements of one array, so we need Amax and not the maximum, which compares the elements of two arrays one by one. Okay, so here we need the Amax, which compares the elements of this vector, which holds the absolute deviations of psi to psi naught. And these are two approximations for the stationary distribution. Okay, now if callback is given, then we invoke this callback function. What should it have? Error, now maybe psi and psi naught, and the iteration count. Okay, if error is less than tolerance, then break. And here's the update for of the object that we are iterating on for the next iteration. And of course here it should be psi naught equals psi. So as you can see, the structure of the solver is exactly the same as in Newton, but I would just add a couple of checks. All right. So first of all, let's make sure that psi naught and p are arrays. NP arrays, just in case they're passed as lists. And I would want to do a couple of asserts. So let's check that the psi naught sums up to 1. How do we do that? Say psi naught sum equals 1. Well, we can't do that because the sum is a float, right? So we need to look at the absolute deviation of the difference. And it should be less than some small constant. Otherwise, we should say initial distribution does not sum to 1. And let's check one more thing, namely that p, the sum along axis 1 is also so every row of p sums up to 1. So this is a stochastic matrix. Now this is going to be a vector, so I'll need np absolute value of the vector. This has to be less than small constant, and I want all of these conditions to be true. So we use np all for that. Otherwise, and this should be it. Okay, we get an error here. Let me go to the normal mode. So what's the error? Name x naught is not defined. Okay, sure. So that was something left from the Newton solver, but where is it? Return. Of course. What do we return once we're done? We return the psi, the last updated version, right? So 0, 3, 2, 5, 3. Here's our answer. All right. That seems to be working. How can we check it? Let's try to modify something here. And now we can just call this function from that cell. Now the function is in the memory, and it doesn't matter that it's in the next cell. Well, P is not stochastic matrix anymore. Okay, that was a good thing to check. So here's another stationary distribution. Now I want to replicate the solution from the last. Oh, everything is equal in this one from the last video. And if I remember correctly, it was something like this. Okay, there we are. So here stationary distribution, as you can see, is not quite 0.4, 0.4, 0.2 that we saw in the last one. So to get the really accurate solution, let's increase tolerance, and here we go. Now let's try to also print something out. Print iter is going to be a function, and I'm using this generic way of passing arguments to the function in Python, which is double stack keyword arguments. And they can be accessed in the following way. This is just going to be print out. I want to say iteration. Iter equals an integer, and then current psi equals, and let's use the generic format for the printout. Okay, and here this quark is just a dictionary. So iter, I think, is what it will have, because we said that iter is going to be, this argument is going to be called iter. And then psi, yeah, they updated. Like this, right? So the iteration will be printed here, and the psi will be printed over here, hopefully. Yeah, that's what we expected. Now, on each iteration, the current approximation of the stationary distribution is printed, and of course after the iteration 0, that's once we already multiplied the initial distribution by a matrix, and then we get the first row, and that's what's here. So how many steps did it take to converge? 25 steps. We could also say max iter is 26 and get the answer within the tolerance level. But if we say something like 20, well, it's still within the tolerance level. So I want to generate an error. So if I make the tolerance really small, and 20 iterations might not be enough to converge to that tolerance. Okay, so this solver works, and this is a successive approximation solver. It takes so many iterations, about 26 iterations, as we saw before in the previous video. Can we do better? This is what we've just written, and this is the version that I've written previously. The only difference here is that I make a default value for psi naught, because it's really not important for successive approximations where you start. So this solver shouldn't be dependent on the initial distribution of the distribution of the initial value. So if it's not given, then it just takes the degenerate distribution that we just used, but it doesn't need to be passed, right? So this one can be invoked with just p. With just p. Oh, I'm out of screen space. And it produces the same sort of output. All right, let's move on. Can we do better? Well, the idea is that we have this condition for the stationary distribution. Think about it. It looks a lot like an equation, doesn't it? So if we move the right-hand side to the left and take the psi star out of the bracket, we almost have a linear system, except that we have the, unconventionally, the x, the unknown, multiplied from the left. Well, if we just transpose this, we get this form. You know, the transpose of the matrix and the difference of the transpose is this. Transpose of the difference of the matrix is the difference of the transpose. Now, of course, the identity matrix, is just going to remain the same. So we only need to transpose P once, and we will get the transpose distribution. This is now a column vector, this psi tilde star. But the thing is that now we can solve this equation with our standard linear solver that we looked at 3 videos ago. Let's try to implement this. So here we are. Disregard this comment yet. M is going to be the shape, the first dimension of P, so that's essentially the number of points in the state space. We will form the A matrix exactly according to the formula. The I is the identity matrix minus the transformed P. And then we just have to solve the system using zeros as the right-hand side. What do we get? Well, we get zeros. Really, if we look at this equation here, you know, is psi star just a vector of zeros, of course, is the solution of this equation. So what's going on? Well, look, here I'm printing the rank of matrix A, and even though we have 3 points in the state space, the rank of the matrix is 2, so the columns of this matrix A are linearly dependent. So we have a rank problem here, and that means that the determinant of A is 0, and the system has multiple solutions. One of them is 0, but we're looking for a different one. We're looking for the one which represents a distribution. So the sum of the elements of the resulting vector should be 1. How can we deal with this problem? Well, there are several approaches to work with this underdetermined systems, but here's a really nice trick that I'd like to discuss, to talk about. Can we add an additional column to the matrix? Remember, this is the original A. Now we want to add an additional column so that the columns of this extended matrix are linearly independent. Well, it appears that we definitely can do that. So if E is a vector of ones, this is a column of ones and this is the row of ones, we can essentially just extend the matrix by 1 column and 1 row and add an additional unknown, which I call epsilon here, such that the last row of the matrix essentially represents the linear restriction, linear constraint on the elements of psi. So look at this. If psi is such that all of the elements sum up to 1, then this last row will produce 1, you know, E transposed multiplied by psi. That's going to be 1 plus 1 times epsilon equals 2. So from this last row, we immediately see that in the solution, epsilon will have to be 1. And in the same time, the elements of psi should sum up to 1 because of this last row. So we're essentially including the linear constraints into the system itself. That's the trick. Okay, let's try to implement this and write some code. And I will use the same checks as we had over here to start with. Right, but now there's not going to be any loop because this is a direct solver. Now this is just a direct solver. So we should just form the matrix A. And I'd like to start with ones because there's an additional column of ones. So now it needs to be, let's say, m plus 1 by m plus 1, where m is just the number of points in the state space. So as before, I can take the first element of the vector shape for P. P is m by m matrix or n by n matrix. And now I want to put into the upper left block of A, I want to put the NPI of M minus P transpose. Now, which block is it going to be? It's going to be all of the elements except for the last one. So up to the last one in both dimensions. Okay, and then B, the vector of the right-hand side on the right-hand side in the system. Well, that's just ones. How many ones? Just M plus 1 ones, and then except for the last element, which should be 2. Right, so this now is exactly the system here, and we can simply give it to the linear solver, which is invoked by np linalg solve a b. Let me just check. Whether we need to give it anything else. No. And what does it return? What does it return? No, it just returns the x. Okay, so this we can just return from the function, just like that. And let's try it out. Stationary linalg with the same inputs. And we get, we get this additional element in the solution. Well, of course, that's the epsilon, and it is 1 as it should have been. All right, so okay, let's say we save this into a result and we return the vector without the last element. So again, from the first one up to the next to last. And that's exactly what we would expect. So let's try it for some other inputs. I'll go back to the cell here where we were playing with the solver. And let's kill that. There's no callback in this direct solver because there are no iterations. I don't really see whether we want to print something out. So let's print both solutions. And here we are. They are producing the same. Well, except that now, if we change the tolerance, say 0.6, 0.8, you know, this is approaching, this successive approximation solution is approaching the solution produced by the exact solver. But it's, you know, you have to be careful with this additional technical parameter, the tolerance level, as you should be careful with the number of the maximum number of iterations. So it's more finicky, right? The successive approximation solver. And as you would guess, that's also much slower. You know, solving a linear system directly is just one operation on matrices, matrix division, whereas the successive approximations, they require lots of matrix multiplication in you know, successively. Just want to try something else. Here we are if the tolerance is not as high, then we get somewhat different results from the two solvers. But we always know that the stationary is the direct one and more accurate one. Okay, that was it for this practical video. There is a nice post on brilliant.org on the same topic if you would like to go a little bit further. See you in the next video.